Want to finish steady state electric current by telling you there's a very unique relationship between the leakage resistance and capacitance. Right? So in another sense, knowing the current value could help you in deriving the resistance. Right? So we take a look at two conductors. It's forming some kind of capacitor, right? We add a battery to support the potential difference. So therefore, the conductor connected to the positive end accumulates positive charges, and negative charges are accumulated on the other conductor. So we know the field lines, the E field lines are generated from the positive end to the negative end. And if you pay the attention to the details, all the lines are normal to the conductor surface, okay, locally. We understand this simple system as a battery or as a capacitor. And we know how to calculate the resulting capacitance. But now the question is, what if in between the two conductors we have some imperfect dielectrics? When the two conductors are separated by imperfect dielectrics, due to the field lines, you might have the potential to allow current, right? So in this case, ideally, if you have two conductors acting like a capacitor, you don't want to have current flowing across the two conductors. But in reality, dielectrics are not ideal, so they do conduct slightly, and thus giving rise to some leakage current, 漏电流, leakage current, which is not intentional, but it might be there. And therefore, when you have the leakage current, you have something called as the leakage resistance. This is not entirely new. If you refresh your memory, when we talked about the transmission line, we actually included the leakage resistance, G prime, conductance per unit length, into consideration, right? So today I want to talk about it, and just to let you know, you have improved a lot, okay? All right, so the capacitance defined by this two conductor is the amount of charge divided by the potential difference. And now that we know Q, the total charge included on a single conductor, is D making a closed surface integration, right? Divergence of D equals rho free. And that gives you this relationship. And voltage, the potential difference, is nothing more than the negative line integration of your E field intensity. So that is purely from the definitions. But D equals epsilon E, because now we're considering in this part where we have leakage current, right? So another way to formulate it is D is associated to charge, but it's also associated to field only. So D equals epsilon E, so we're just replacing the definition of D and E. And the bottom remains unchanged, okay? What about resistance? Resistance is defined as the potential difference divided by the current value. As I stated, ideally, if you have a perfect capacitor, ideally there would be no current flowing across the two conductors, right? Ideally, if you have vacuum or you have perfect insulators, you don't have current flowing. But in the reality, you might be using a material that is slightly conductive to serve as your filler or displacer, right? You have to fix the two conductors in space. And that filling material might be slightly conductive, although it is a dielectric, so you have a small amount of current flowing across the two conductors. Therefore, you have some kind of leakage current, right? So once you have the leakage current, you have leakage resistance, right? So the potential difference is still defined as the negative line integration of your E-field intensity. But I, your leakage current in this case, is nothing more than the leakage current density making a closed surface integration. So again, this is purely from the definitions. I is current density making a closed surface integration. But we know J equals sigma E. Once you have a conductive material, you can just take the consideration by knowing its conductivity, sigma. Okay? Now, as we compare the top and bottom, on the top, we're trying to evaluate capacitance. At the bottom, we're trying to evaluate the leakage resistance in this system. Somehow, we see there are common parts, right? We both have voltage, but one is in the denominator and one is on the numerator. So is there any way we can eliminate the effect of V, the potential difference? Well, we can eliminate the presence of V by multiplying capacitance to resistance, right? If we multiply these two quantities, this one is canceled by this one, and then in the numerator, we have the closed surface integration of epsilon E, and in the denominator, we have the closed surface integration of sigma E. And this integration, they are both calculated over the same surface. So basically, point by point, you have an evaluation of the epsilon to sigma ratio. So this is telling you, if you have a capacitor, right, with a known capacitance, and you have some kind of leakage current, you know there will be, unfortunately, some leakage resistance. Do you need to do additional calculations? No. All you have to do is, well, you know the material parameters, right? You know the dielectric materials permittivity and conductivity. Therefore, this ratio is actually known. All you have to do is you find out the capacitance of the system, and then you have the leakage resistance. Okay? You take the ratio of epsilon to sigma, and you divide it by C, then you have the leakage resistance. A very simple and straightforward way to find out the leakage resistance. Why is this helpful? If you still remember this simple coaxial cable, which we derived for its capacitance value, right? If you still remember, the capacitance value is 2 pi epsilon. Epsilon means the permittivity of the material filling between the two conductors. But if in the practical sense, that dielectric is slightly conductive, so it's also having, well, in addition to epsilon, it is also having a slight conductivity, sigma. Then you don't need to do additional calculation. By our previous finding, R times C equals the ratio of epsilon to sigma, you directly find the leakage resistance. Well, if you don't believe me, let's come back to this table again for the transmission line. In the past, well, I showed you this to convince you that you have made abundant progress. You are now able to find the capacitance per unit length for this given coaxial transmission line. And now you have the capability to find out the leakage resistance, which was labeled in transmission line as G prime, right? Exactly the same result, right? G prime is the inverse of R, right? So you take the inverse, you have this result. So after 8 weeks, right, I'm showing you are understanding more and more. Initially, you were forced to believe the transmission line can be represented by 4 basic elements: resistance, inductance, conductance, and capacitance. But now it's corroborated, right? Turn by turn, you have the ability to derive its resulting values, right? And that's what I call progress. So do you have questions? If not, I'm going to close E fields, and we're moving on to magnetic fields. Right. Of the textbook, we are going to discuss about static magnetic fields. First, in free space, there's nothing, okay? And then for the next PowerPoint set, we're going to talk about static magnetic fields, but having materials. And then in the third PowerPoint set, we're going to talk about the boundary conditions and the energies associated with magnetic fields, right? But before I start, I have to warn you. Throughout experience, most students find this part difficult. And the reason is, to understand about magnetic field requires some imagination, but in a practical sense, you have to review and understand vector operations carefully, okay? Whenever we talk about magnetic fields, there are a lot of mathematical procedures involved, and especially a lot of curl operations. So please do go back to the video or the lecture notes for vector operations, divergence and curl, especially curl. Okay? So in this PowerPoint set, again, this is a new field quantity. So we are going to talk about the fundamental postulates first. I will spend a considerable amount of time to talk about it. And then we are going to introduce something called the vector magnetic potential. This is something you're not accustomed with. In our daily lives, we are very familiar with electrical potential. voltage, right? We use batteries every day, but we don't really know, we don't have daily life experience with magnetic potential. So this is purely, like imagination for most of the students. And I have to confess, vector magnetic potential is something really mathematical. So after today, over the weekend, please do review vector analysis, all right? And then we're going to talk about Biot-Savart law. I don't really speak French, but I don't know why. Magnetic fields are associated with a lot of French scientists. So I do practice pronouncing the names of these French scientists. So last year, I was very fortunate. I had 2 or 3 French students on exchange. So hopefully, I'm pronouncing the names correctly, right? And for the very last part of this PowerPoint set, we are going to talk about magnetic dipole. Now, in the past, I spent a lot of time teaching you electric dipoles. But now, when we move into magnetic fields, we also have a counterpart, something called magnetic dipole. So after the introduction and discussion of magnetic dipole, we are going to compare the 2 dipoles side by side. All right? Okay, fundamental postulates. Again, whenever we talk about the field postulates, we will talk about the postulates in 2 forms. One is in the differential form, having divergence or curl. Another one is integration form. You have closed surface integration or you have the volume integration, right? Then we will talk about the application of the Ampere's circuital law. In Chinese, we pronounce it Ampere, but to my best knowledge, in French, it's Ampere. Okay, this R is R. Okay? Okay, so before we really move on, I think in high school, especially in the very last year of your high school year, we were forced to believe if we have magnetic field present in space and we have a charged particle moving at certain velocity, that particle would undergo some circular motion, right? And that associated force is called the Lorentz force. So that is your first encounter with magnetic field, right? So Lorentz force, Fm, is the charge carried by the particle and then multiplied by the velocity making a cross product with the magnetic field. What does that mean? Now, if I have a charged particle, Q, moving at certain velocity, but in space, I have magnetic field, right? This particle will feel a force in the direction and quantity defined by U cross B. So this force is a vector, right? So basically this particle would change its trajectory and goes out towards your eyes, okay? And as it changes location, it will undergo a cyclotronic trajectory, right? But this is something known to you, and it's called Lorentz force.